1/3 of a meter to be reduced in a forging press by uniaxial compression. The press can develop a force equivalent to 10,000 tons. Write down the stress tensor and determine the deviatory and easy stress. So quite straightforward. In a uniaxial test, the material initially yields at -70, so this is the initial yield condition, and hardens linearly before fracturing at -1,000 megapascal, and a plastic strain of 100%. Sketch and label the graph of easy stress against equivalent plastic strain, and hence find the equivalent plastic strain produced by the forging operation. Determine the plastic strain increment tensor. Right, let's try to imagine what's going on here first. So last time we have now a steel billet. So we saw that example, so it's going to be compressed. So one side is very long, so it's basically a plane strain condition, wherein the strain on one side is equal to 0. How are we going to solve this one? What we're going to look at here is look into a more realistic condition wherein what's the force acting here, and the force acting here, and the force acting here. So if we have this one to be in the second direction, I'll just try to follow his, we call this one axis. Right. So this is your steel, and then you have your compressive forces there. So this one is 100,000 tons. Yes, and you multiply this one with 10, so that's 1 million newtons. So 1 million newtons is that 1,000. Oh, this one is okay. Pounds times 1,000 in kilograms. That's in kilograms. So multiplied by 10. That's 1 billion. So we have this one to be 100 meganewton. Am I right to say no? 10,000. Sorry. 10,000. There you go. Change. 10,000 tons. That will now be kilograms. Multiplied by 10. That's 100 million newtons, which is 100 meganewton. Right. This one now. So this one is. So each side will be 1/3 of a meter, and then this one will also be 1/3 of a meter. So sorry, my copy is wrong. Okay. So this is wrong. I think it will be more along the length. Can you change that? So. Something like that. So it's the same. You have your force equal to kilograms, 100 meganewton. divided by area is 1/3 times 1/3. That will now be in meters squared. So what do we get? So 900 times 10 to the 6 Newton per meter squared, or 900 megapascal. Okay, we got it? So let's look at this one here. Let's write our axes. So our axis will be, say, that one is 2. I'm just trying to use 2 there, sigma 2, 2. So let's look at our axis here. 1, 2, 3. Or, yeah, it's probably going to be like this one here. 1, 2, and 3. Wherein we don't have any force acting along axis 1 and 3. So if we don't have any force acting along axis 1 and 3, then we have the stresses to be 0, and then your stress here will be equal to sigma 2, 2. Is that okay? So from here, sigma 1, 1 equal to 0. Sigma 2, 2 is equal to this compressive stress minus 900 megapascal, because it's acting along the 2 direction, and then the stress along this 3rd direction is equal to 0. What about the shear stresses? What about the shear stresses? Any question? Any comments about the shear stresses? So the shear stresses are equal to 0 because there are no other forces other than what we have here. So the others are basically 0. So if we're going to write our state of stress, sigma ij, sigma 1, 1, 1, 2, 1, 3. This one is symmetric. Then of course they are 0, 0, 0, and then you have here minus 900. So that is your state of stress. This also indicates that this one now will be your principal stress. It's compressive, so that's minus, so that is now sigma 3. Okay, maximum principal stress is actually 0, but who will be 0 whenever you're calculating that? You have to consider this one to be now your stress acting on your material. Now, the next thing that we're going to look at here, so we have now determined the stress tensor, determine the deviatoric and the Mises stress. What's the Mises stress? Yeah. So let's write the von Mises stress. The von Mises stress, since we already know that this one is also your principal stress, perhaps you can now just use the principal stress values without the shear anymore, so you can ignore that. So that's sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. So see what happens really. this one here. So what do you have? So this is 0, that's 0, that's 0, 2 square root, 2 sigma 3 square root. Take the square root of square root. Okay?
But why 0?
So this sigma misses is simply equal to that sigma 3, which is equal to 900, sorry. Minus, that's minus 900, sorry. So that's minus there. That's still minus 900. You square it, so let's have a look. So this one is minus, so that's so minus 8 minus 900, so that's still positive. Thank you. Any more? Sigma 1 misses. Deviatory stress. What's the deviatory stress? So let's say, for example, deviatory stress tensor. What's that? So what is your hydrostatic stress first? So you know that your deviatory stress tensor is equal to what? Your sigma ij minus 1/3 sigma kk delta ij.
1/3, right? 1/2.
Right? So this one is also
You always make a lot of mistakes. A lot of mistakes.
okay.
You realize?
And then your sigma h is equal to sigma 11, sigma 22, sigma 33 divided by 3. That's 0, that's 0, that's minus 9, minus 300, minus 900, so minus 900 divided by 3 minus 300. Symmetric. So you get this one, put it in here, you get this value, then you get your deviatory stress tensor. So your deviatory stress tensor this is now your deviatory stress tensor. 300 minus 600, and then you have a 300 here. Okay, so that's your deviatory stress tensor. That will be in megapascal. So anyway, what we're doing is just, end of the day, we just want to get this plastic strain influence before solving it, or solving some problems in plasticity. Next. that we need to solve is the so this one here, the second one. In the uniaxial compression test, the material initially yields at minus 750 megapascal. Initially yield, so this is where your yielding starts and collapse at negative 1000 megapascal. And this one will be your plastic strain 100%. So meaning from 0 plastic strain to 100% plastic strain. Sketch and label the graph of Mises stress against equivalent plastic strain, and hence find the equivalent plastic strain produced by the forging operation. Equivalent plastic strain. So what is our equivalent plastic strain? Now remember our graph, right? We have a graph wherein after you yield, then you have now also your stress strain curve. Right? We have now here plastic strain, so I'm just going to have here plastic strain and then your 1 meter stress. So I start from here, okay, and this one is 750 megapascal, and then it goes up to 1000 megapascal. So I'm just trying to work on this one here. So that's negative. Our actual stress, sigma 22, is minus 900, or we're working on the 1 Mises, so all of these must be in the positive range. So we have 750 megapascal to 1000 megapascal, and our 1 Mises is 900. And then we have now here from 0% strain to 100% strain. So nothing much, it's just a linear movement. There you go. So we're looking at this one. I think the term there is strain equivalent. Ratio proportion. Yes. So this minus that divided by this one is equal to that. This minus that divided by that equal to that divided by 1 or 100%. How about that? So your equivalent strain is equal to 900 minus 750 divided by that 1000 minus 750. This one is multiplied by 100% or 1. Yes? So this one now is what? You have 150 divided by 250, 3 over 5. So that will be 0.6. So that is your equivalent strain. So reason is that from here you have now your strain and your stress strain. Okay, so your yielding starts at 750. That's where your 0% strain will be. And then this one goes up to 1,000 megapascal where you have collapse. And that's where your 100% will be. So draw a line. You have your one pieces at the moment to be 900 megapascal. So you can get this turbulent strain. And then finally, determine the plastic strain increment. Plastic strain increment. What is the plastic strain increment? I'm just going to use that equation there. The plastic strain increment is equal to d half of the equivalent. Sometimes it's really confusing. Divided by your one means stress multiplied by your deviatory stress. Right? One means is 900. You were able to get your deviatory stress. You can now solve for this one. It's quite straightforward. What's the unit of this plastic strain? What's the unit of this one? Still big, isn't it? It's a unit strain, but still large. Anyway, probably because it's almost towards the collapse. This one is unitless. Strain is unitless, right? If we try by definition, strain is the displacement divided by the total length. So that's unitless. So this plastic strain increment is also unitless. Have a look at this one here. This one is strain in megapascal, stress in megapascal. This one is in megapascal. They cancel out. So it's unitless. Okay?
You got the one on DEP IG.
Yeah.
I thought it's the power. Lousy player.
Oh, you should give it.
Lousy. Lousy, lousy.
So your project one is plate with a hole, is it? Plate with a hole.
With the hole. With the hole.
So because of the problem of symmetry, your project one or project assignment one, you just take a quarter of this one because of symmetry. Yes?
Yep. He like Dutch player.
If you're having a problem with the abacus, I think if you go to CSM, you will be able to see there some basic tutorials. It's given as a code, so all you have to do is to input it in abacus, and then after that open abacus, and then come up with the data. So it's very straightforward. So the problem that you have at the moment is a plate with a hole. Yes? Because it's symmetric in two axes, then you're just looking into this problem. Yes, so that's the only problem there. So what's the loading like? Vertical, horizontal? Going down, upward. So you will have some rollers there, yes? So meaning it's going up, and this one here. Okay? Question. Where do you think will be the maximum stress? So say for example, this one is point A, that is point B. Why is that so? Okay. What will be? The question here is if that will be. So what's the direction of your maximum stress? Going up or going sidewards or the stress? Downwards. That's one, that's two. You have. Everybody? Going one, going two, plus two, minus two, minus two. Why? Why? And if that is your stress, what will happen to your one business stress? What will be your stress of one? If you have your maximum stress here, or here, supposed to be. What will be the value of your other stress? Well, the reason I'm telling this one is that actually this one can help. Have you seen your notes already? Obviously, you haven't seen it yet. So I don't know why Dr. Rob Thompson put it here, but probably because of this part. But anyway, this part here, section 1 actually can help a lot already. Sigma 2, is this one going up or going down? Because your direction is going up. Your stress will go up. What's the distribution like? What's the stress distribution like at this point here? The reason is that for this hole here, because if you apply a stress, right, it will be distributed here. So you have a distribution here. You have a distribution there of stress, right, of your force. So stress will be distributed. So if you move here, it's still distributed. Right? But here, when you go here, what happens? So you have no one here carrying. So for example, there's say 6 of you pushing that truck, and 2 in the middle are pretending to be pushing it. So who will carry the burden? The one next to them, not the one to the end, yes? So which one here will carry the burden? The one next to this one. Because this hole here is not carrying any load. So that person next to this hole here will be the one who will be burdened by taking that stress. And then as you go away, as you move along, or as you move far from this one here, then it normalizes. So like I said, if your a lot of you are pushing that bus. And then the ones in the middle are just pretending that the ones near that middle are the ones who's going to really be pushing more than the ones who are farther to those people who are pretending to push that bus. Okay? So it's the same principle here. So what happened is that in this case, you probably have that. You can have a look, and then it tapers there, normalizes. So as you can see, who's carrying the load? So it's basically those near the pole. Okay, there are tutorials in Abacus, in CSM, it's called them. If you're not familiar, try to play around. So many tutorials in Abacus. You can download the, I think the student version is more than enough for this one. Student version, so you can do it at home. Any questions so far for this one? So I think this one will be a very helpful information, though I don't think this one will be helpful. Is this colored in the, is this one colored in the soft copy? So this probably will help a lot. Questions? So that ends our plasticity. We'll have sessions on finite elements next week. I won't be here on Monday. We'll have our sessions on Thursday then. Okay, in the afternoon. Any questions so far?